Good evening, students. Lecture 15 is about statistical and unsupervised learning, in which we are going to describe the role of data and statistics in machine learning. What are some of the important statistical parameters in this regard, and how can we perform learning when the data labels are missing? A long list of agenda items include statistical learning and its types. Most importantly, we're going to talk about the Bayesian learning and its different forms and simplifications, such as map learning, the maximum likelihood, log likelihood learning. And then we're going to discuss non-parametric learning, such as K nearest neighbor learning, and how can one estimate density function using K nearest neighbor method. And in the end, we're going to describe different forms of unsupervised clustering, such as K-means clustering and learning Gaussian mixture models. All right, let's begin with statistical learning. So in this case, we are given a set of observations, data, and also a set of hypotheses. And our goal is to find out which hypothesis is more or most consistent with the data, observation, or the evidence. The most important type of statistical learning is the Bayesian learning. And Bayesian learning actually utilizes the Bayes theorem and tries to compute the probability of any hypothesis hi being correct given a set of data, d in this case. So essentially we are interested in finding out this conditional probability p hi given d. The hypothesis h that maximizes this conditional probability, that is probability of a hypothesis being true given data, is then used to make prediction about the future or the unseen data, or to make decisions. Now, I would like to bring your attention to one of the most renowned application of Bayesian learning in mechatronic engineering, and that is the SLAM problem. So I would like you to recall the SLAM problem we discussed in detail and at length before the midterm examination. So essentially, the hypothesis in the Bayesian learning that actually is going to map to the robot location or the orientation. We'll just call this as L. And the other hypothesis was about the environment. Now remember, these two variables, L and M, they represent a hidden data. So essentially they were a hidden variable that we were trying to estimate. And we were trying to estimate them based upon the data. In case of SLAM, the data was the output of the sensor. And if you can recall the mathematical description of the SLAM problem, then the conditional probability, that is PLM given O, meaning that we were trying to guess the position of the robot, and accordingly we were trying to guess the map of the environment based upon the data. So the data, which is the sensor output, will be known or given, and we simplified this whole expression using the Bayes rule or the Bayes theorem. And our job was to somehow maximize this conditional probability so that the best possible estimate of the environment map could be made. And obviously, to obtain the best possible estimate of the environment map, we needed to simultaneously correct the robot location and its orientation. So after correcting the robot location orientation, at the next step, a precise, or you can say that a better or a more precise environment map was constructed or updated. Now, Bayesian learning makes a remarkable tool in machine learning, and it exhibits some key merits, including but not limited to the avoidance of overfitting and to be able to perform even when the data is noisy or incomplete. We talked about the unsupervised learning paradigm in which the data labels are missing. And one of the key advantages of Bayesian learning is the unsupervised learning. Now, why is it that Bayesian learning is so powerful in avoiding overfitting and dealing with the incomplete data? And to my understanding, the main reason is that because Bayesian learning utilizes the power of probabilistic models. So everything is modeled using probabilities, such as the position and the orientation of the robot, the output of the sensor, and the perceived map of the environment. All of these variables are actually random variables. And because probabilistic models are very flexible models, they can subsume wide range of uncertainties, and if they are tuned and updated carefully, then they can easily avoid overfitting, and they can work with incomplete and noisy data. They can actually perform filtration as well. So let us describe Bayesian learning more mathematically. So H defines the set of hypotheses. It's a set of hypotheses Hi, and there can be, say, small n number of hypotheses. D is a set of data points. Di represents single data point, and suppose we have up to capital N number of data points to work with. In Bayesian learning, we wish to compute the conditional probability Hi given D, and we're going to compute this conditional probability with the help of Bayes' rule. So Hi given D equals Pd given Hi, probability of Hi divided by probability of D. We can make a simplification here by dropping the denominator, and if you remember, we call this as common denominator. It is because for all different Hi, this denominator P of D remains the same. That's why a common denominator. So if we drop that, we get probability Hi given D tilde, which equals a product of 2 times probability D given Hi and probability of Hi. And this probability is an unnormalized value of probability Hi given D. So tilde represents unnormalized value. And this can be normalized and corrected by bringing back the common denominator, and that common denominator can be computed by the formula given here. So in a sense, we are just going to normalize this value by dividing probability Hi given D tilde with the sum of probability Hj given D tilde for all the values of j going from 1 to n. Alright, so once we have computed this conditional probability of a hypothesis given data, then as part of our testing process or prediction in this case, suppose we are given an unseen data x. So this is a single data point x which was not present in D. So D was essentially the data set for training, and x is the single data points that is used for testing or prediction. So our job is to find out the probability of x given d, meaning that what is our best guess about x given the data that has been used to train the system and to update the conditional probability of hypothesis. So in other words, once we have trained our system using the data set D, what can we say about, or what can we predict about the unseen data point X? That is the problem at hand. And this probability expression can again be solved either by using Bayes' theorem or just by applying the law of total probability, although in this case we are using the law of total probability, and the final expression will be in the form of summation of product. So probability x given d equals summation I1 to n, probability x given hi, and probability hi given d. So in some sense, we are trying to predict the label of x. And it is important to note that the label in this case is associated with the hypothesis. Right? So as we discussed earlier, that in case of Bayesian learning, and this is one of the remarkable attributes of the Bayesian learning, that it can work without the label of x. So yes, we have made some guess about x, but the actual label may be unknown. Therefore, it makes a lot of sense to keep all possible labels of x along with their corresponding probabilities, which is p. Suppose in this case, if x can have range of values, x equals to 0, probability x is equal to 0 given d, probability x is equal to 1 given d, and probability x is equal to 2 given d. So we would like to keep all those values and corresponding probabilities for our computation and future processing in our record. So that's exactly what we are saying here, that when the data labels are not given, then we would like to store and update the probabilities of the corresponding data labels. Now, the important thing to note over here is that the probability will be in the form of probability density or probability mass functions, and those are specifically referring to the probability hi given d. So in some sense, when we talk about the data labels here, because actual labels may not be given, so we are associating data labels with hypotheses. That is the main point to understand here. We're going to store these probabilities for all possible data labels, means for all possible hypotheses. Then the update is based on the latest prediction of the data labels as well as the new data point x. So this updation is the updation of these probabilities, probability hi given d. So what we're saying here is that we are going to update this probability based upon the data that we have seen already, that is d, and we're also going to utilize the unseen data points. So we are actually adding our unseen data points to our data set, and we're going to update this probability, and that's exactly how the unsupervised learning works. So in summary, what we have just said is that in unsupervised learning, the data labels are missing, and we are going to assume that data labels actually are the hypothesis. They map to hypothesis. So the number of labels equals the number of hypotheses in this case. time for some basic definitions here. P probability hi given d tilde equals probability d given hi times probability of hi. So the two terms, two probability terms have a special meaning. So let's look at first probability hi. What is the probability of hypothesis? So PHI is called the prior probabilities, and they are needed to be assumed in the beginning. And there's a lot of research and work that has gone into deciding how can we choose an appropriate prior probability to start our machine learning algorithm, in this case Bayesian machine learning. But one rule, a generic rule, is that we should try to choose probability hi in view of avoiding an overfitting. So for that, we would like to assign lower prior probabilities to complex or complicated hypotheses. On the other hand, we would like to assign higher probabilities to the simpler hypothesis, and that is perfectly consistent with the Occam's razor, which says that the simplest explanation or the simplest hypothesis that explains the data is the best hypothesis. So this is a generic rule that one can follow at the time of choosing the prior probabilities that we need to assume in the beginning of the Bayesian learning algorithm. Then there is probability of data given the hypothesis. So for given hypothesis, what is the probability that we are going to observe the data, which is usually in the form of the sequence of data points, as we shall see shortly. This can be easily computed, or it is known a priori, or it will be given, and it will be further demonstrated in the example that we are going to do shortly. So that is not much of a concern. So what we have seen here is that we need to assume the prior probabilities, and we have a rule to avoid overfitting. Then the other probability, the probability of data given hypothesis, that will be given, or that can be computed quite efficiently. The last definition here is the posterior probability. So posterior probability is what we need to store and update in each iteration of the Bayesian learning or its variants. So essentially, the posterior probability is proportional to the product of the prior probability and the probability of data given hi. And this posterior probability will be updated with each new data point, and it may also, you can also substitute the prior probability with the posterior for the next update, depending upon the application. We said that the probability data given hypothesis could be computed efficiently, and one of the assumptions that goes into the simplification of the computation is the Iid assumption. So Iid stands for independent and identically distributed data. So independent and identically distributed data points. So as a consequence, when we try to compute this probability of data given hi, and this data is actually a sequence of data points starting from di, d2, and ends in d capital N. This actually maps to a joint probability of d1, d2, d3 all the way to dn given hi. One can split this joint probability into a product of marginal probabilities, which are probability d1, probability of d2, probability of d3, probability of dn, and all of these probabilities are conditioned on the hypothesis. So by breaking or decomposing this joint probability into a product of these marginal probabilities, will simplify the calculation or the computation of the conditional probability of data given hi. So that's why one of the reasons that we like to make assumptions about the independence and the identical distribution of the data points is that in practical applications, this assumptions is very realistic and therefore significantly simplifies the computation. Also, we would like to assume so one condition is the independence. The data points are actually so all of these data points d1, d2, d3, and dn, we're saying that they are independent. They don't have any mutual correlations. The other aspect is the identical. What do we mean by this identical? In a sense, this last ID means the identical distribution. So we're saying that all these data points, they have been sampled from the identical or same probability density or the mass function, and that's completely described by hi. So I give you an example. So if what do we mean by the identical distribution data points? It means that the probability of data point 1 to be true given hi is the same as the probability that data point 2 is true given hi, and this is same as the probability that nth data point has true value given hi. Likewise, the probability that any data point has false value given hi is the same regardless of the index of the data point. So that is the meaning of the identical distribution. One can describe the pseudocode of Bayesian learning algorithm as follows. Initialize the prior probabilities phi, and we're going to initialize a variable denominator. So this is the common denominator that will be used for the normalization of the posterior probabilities. Then the main body of the algorithm has two loops. So the outer loop is iterating over hypothesis. The inner loop is iterating over the data points. So once for each hypothesis, we're going to initialize probability d given hi to 1. And then for each data point, we're going to update probability d given hi as probability d given hi, the previous value, multiplied by probability dj given ha. So this is again coming from the Iid assumption. And so once this updation is complete for all the data points, then we update the posterior probability of the hypothesis hi given the data by using the equation of Bayesian learning. And we're going to update the denominator, which contains, which is essentially accumulating all the posterior probabilities. So therefore, the scope of this denominator update lies within the outer loop. So once the outer loop finishes or ends, we are going to finally normalize the posterior probabilities phi given d by dividing them with the denominator, common denominator. Likewise, it is easy to compute the probabilities on the future data points, probability x given d, where d is now the past data if in the context of x being treated as the unseen or the future data. And that probability can be computed easily once we have the information of the posterior probability hi given d in particular. So to understand these concepts, let's take the candy example discussed in the textbook. Imagine a bag full of candies which come in two flavors, the cherry flavor and the lime flavor. A bag contains several candies, but we don't know what fraction of each candy flavor is present in the bag. And this is our job, to estimate the fraction of each flavor based upon our sample data, which in this case will be randomly selecting a candy from the bag and then tasting it to determine the flavor. So the data point in this scenario is going to represent the flavor of the candy, which can have two possible values, the cherry and the lime. But one of the things you need to be careful of in this example is that cherry or the lime flavor represents the data value. It is not representing the label of the data. The labels will actually come from the hypothesis. So we are going to make assumptions about the fraction of the candies of each flavor based upon 5 hypotheses, H1 through H5. The first hypothesis, H1, says that the bag contains only cherry flavored candies. The fifth hypothesis says that the bag contains only lime flavored candies. H2 says 75% cherry flavored candies. H3 says 50% cherry flavored candies, and H4 says 25% cherry flavored candies. So based upon these hypotheses and the data probabilities that we can derive from these hypotheses, and we're going to show that in the next slide, our job will be to compute the posterior probabilities. We'll be given the data point values. That is, we will be given a set of data points, and each data point is going to represent the flavor of the candy. In the context of this experiment, the data point actually comes from sampling, more specifically randomly selecting some number of candies from the bag, testing them for their flavor, and then make updates to our hypothesis. So for example, if we do an experiment with n sample candies from the bag, so first sample may be lime, the second sample may be the cherry flavored candies, third may be lime, nth may be lime, and so on and so forth. In order to be more explicit about how do we actually obtain these probabilities P, D, I given H, because these probabilities are required for the computation of the posterior probabilities that we wish to update in the algorithm. So we're denoting X to represent the unseen data point, and DI represents the seen data point, so the data point that we have, that the data, it is one of the data points available in our data set for the training purposes. And so the probability that any data point equals to cherry means that a randomly selected candy has a cherry flavor, given that hypothesis 1 is true. That probability equals to 1, because if hypothesis 1 is true, then the bag contains only cherry flavored candies. So a randomly selected candy will have a cherry flavor with unity probability, and there is no chance of sampling a lime flavored candy when the hypothesis 1 is correct. So that's 0. So probability x equals to cherry given h2 will be 0.75. This is based upon the description of the problem given in the last slide. This probability is 0.75 because hypothesis 2 says that the bag contains 75% candies with a cherry flavor. So any randomly selected candy has a cherry flavor. When hypothesis 2 is correct, that probability is 0.75. And likewise, we have written here the remainder of these probabilities. The last one says hypothesis 5 is correct. Then tell me what is the probability that a randomly selected candy has a cherry flavor. That is 0, because hypothesis 5 says that the bag contains only lime flavored candies. Just before I show you the results of applying Bayesian learning methodology to the candy problem, I would like to remind that it is the same Bayesian learning algorithm that we have seen before, and this algorithm is going to generate the results that we are going to discuss in the next slide. Let us discuss the candy problem in detail. We're looking at the graphs taken from the textbook. These are generated from 10 data points. Each data point corresponds to the flavor of a candy which is randomly selected from the candy bag. For this particular case, we're assuming that all 10 candies were found to have a lime flavor. So if we now run the algorithm for the Bayesian learning, we're going to have 5 posterior probabilities that need to be updated in each iteration. So essentially, we are going to start with the prior probabilities. Initially, prior and the posterior probabilities, they are the same, and so we're saying that the likelihood of this point, the 0.4 probability, that actually corresponds to the third hypothesis, H3, which says the bag contains 50% of the candies with the lime flavor and the remaining 50% with the cherry flavor. So that is given initial higher prior probability over here. And the hypothesis which split the flavor in 75-25 or 25-75, either way, are given initial probabilities, the prior probabilities, to be 0.2, and the hypotheses such as hypothesis 1 and 5, which make a very bold assumption the bag either contains all candies with lime flavor or the bag contains all candies with the cherry flavor. They are given the least prior probabilities here. So if we start with the prior probabilities, then each iteration which correspond to the data points here. So maybe it's not iteration. So we're saying that if we are shown the first data point, and obviously the data point contains the lime candy, the posterior will be updated as follows. So you will see that as more and more data points come in, and we observe the flavor to be the lime flavor, then our hypothesis 5 will have an increasing probability, and the other hypothesis H1 through H4 are showing a decreasing trend of probabilities. So as more evidence arrive, eventually we are going to favor the fifth hypothesis, which says that the bag contains all lime candies, will have the highest probabilities, whereas the probabilities of the other hypothesis is going to shrink and reduce to 0 eventually. So this probability H5 given D is approaching 1, and the other probabilities are approaching 0. We can also plot the probability of x given d here in this graph. So this x is actually set equals to lime. So we are really asking what is the probability that the 11th, if we are here, we are really asking what is the probability that after watching 10 candy flavors to be lime, what is the probability that the 11th one will also be lime flavor candy? That's probability x given d. So we can make prediction after each observation. So this is the prediction made after the first observation, that is after selecting the candy, and it found, and we find that the candy has a lime flavor. Then what is the probability that the next candy will also have a lime flavor? So that's plotted here. After 2 observations, the probability increases, and it is monotonically increasing as you can see over here. And so our belief that the next candy will have a lime flavor will keep on increasing after watching more and more lime candies in this experiment. A simplification to the Bayesian learning, in which we are going to keep only one hypothesis which has the highest probability and discarding all other hypotheses. Such a form of Bayesian learning is known as maximum a priori or map learning. Instead of using all hypotheses to predict the unseen data point, in map learning we use the most likely hypothesis H map in the expression probability x given d. So if you expand the expression of probability x given d by substituting hi with h map in probability x given hi. So previously this expression was probability x given hi. Now hi has been replaced by h map multiplied by probability hi given d. So moving summation inside reduces the second term in the product to 1, and the final expression is just probability x given h map that equals or approximately equals probability x given d. H map is the hypothesis which maximizes this posterior probability. So such a hypothesis is the maximum a priori hypothesis, and this type of learning is somewhat dangerous. It makes a bolder prediction about the unseen data points, especially if hypotheses other than H map do not have low enough probability. So one of the hidden message in the map learning is that we're really banking on one hypothesis to make prediction. That hypothesis is H map, and we are saying that all other hypotheses have negligible likelihood, so therefore they are discarded. As a consequence of this assumption, the computation becomes particularly easy, and the whole process of learning becomes simplified, though at the cost of making somewhat dangerous prediction about the unseen data. We can further simplify the map learning by assuming that all the probabilities they are equal. In that case, the expression for the H map, which is originally the argmax over hi probability hi given d, that is the hypothesis which maximizes the posterior probability. This expression involves the product of probability data given hi multiplied by the prior probabilities. Assuming that all the prior probabilities they are equal and they are equal to some constant, then this constant doesn't count in this maximization problem, and therefore the remaining maximization is over probability data given hypothesis. Such a type of learning is known as the maximum likelihood learning, or the ML learning. The defining characteristic of the maximum likelihood learning is that this is very data-centric learning. It doesn't take into account the uneven prior probabilities, and it is based upon, and it is also, just like map learning, it is also discarding it is keeping only one hypothesis and discarding the rest. So it is making another bold assumption based upon the uniform or equal hypothesis probabilities. This simplification that gives us the maximum likelihood learning works very efficiently and very accurately when we have a sufficiently large data. And it turns out that if we have large enough data, then whatever initial bias we have in terms of the prior probability, so whatever hypothesis we were favoring in the beginning of the algorithm, that is all going to be neutralized by the actual data. So the data is going to dictate our posterior probabilities as well as the maximum likely, the most likely hypothesis H map. All right, let's do a couple of examples of the maximum likelihood learning. The most common type of learning reduces to the problem of learning the parameters which define the hypothesis space. So we are assuming that instead of having a discrete set or a set of discrete or different hypotheses, we have a continuous range of hypotheses h theta, and this theta appearing in the subscript of h defines the fraction of cherry candies. We are referring to the same candy problem. So remember once again that theta represents the fraction of cherry candies in the bag, and we don't know what is that fraction, and we wish to learn the value of theta. And once we know the value of theta, then obviously that from that we can compute the hypothesis or the corresponding hypothesis probability. So theta, because it is a fraction, can acquire a value in the interval between 0 and 1, and we wish to compute theta as we have just described using the maximum likelihood learning. So we start by writing the expression for the posterior, which is the same as probability data given h theta. So we are that is actually equal to the posterior probability h theta given d, because the prior probability has been ruled out. Applying the Iid assumption, because this d is actually a set of data points, it contains multiple data points, so this joint probability according to the Iid assumption splits into the product of marginal probabilities pdj given h theta, the product of these probabilities ranging from I equals to 1, sorry, that really should have been j, so j equals to 1 to n. Now suppose that we take capital N number of candies out of the bag, so and capital N also defines the number of data points, in this case the flavor of the candy, and out of those n candies we have L lime candies and C cherry candies flavors. Therefore if you plug in this value, the product simplifies to the expression which is a product of theta to the power c and 1 minus theta to the power L. So this is so we need to understand how did we get this product. Well, if we say that out of those n we have L lime candies, then the probability of a lime candy is 1 minus theta, and the probability of obtaining the cherry candy is actually theta. So one of the nice things that we have done already is that we have normalized theta, and we are restricting its value between 0 and 1 so that it corresponds to the probabilities. So it's a clever way to relate theta with the probabilities. So and theta has been raised to the power c because it corresponds to the number of cherry candy c, and 1 minus theta is the probability that we have L lime candies in the bag, in the data set. So how can we compute the value of theta? What is the value of theta that maximizes this conditional probability? So direct maximization is difficult. Instead, what we do is that we are going to take the logarithm of this expression, and then we are going to find the maxima of this logarithm, and the value of theta, or h theta, that maximizes the value of this logarithm will give us the value theta in this case that maximizes the probability d given h. So we wish to maximize this value over here. The nice thing about taking logarithm is that the calculation of maxima becomes particularly easier. So if you take the derivative of L with respect to theta and set that derivative equals to 0, you get theta equals to c over n. Once we take the log of this probability, then this type of maximum likelihood learning is known as the log likelihood. So that's how the log likelihood learning is defined. It's just the logarithm of the conditional probability d given h. So that's if you take a logarithm of this quantity, it defines the log likelihood learning.